Okay, so today we are going to see a new algorithm designing technique. We call that dynamic programming. Okay, this is another. So we have seen divide and conquer approach. We know how to analyze the running times of divide and conquer approach. Today we're going to see another different algorithm designing technique. Um, and that technique is called dynamic programming. Okay? So I'll straight away, so I'll not tell you anything about this technique first of all, but I'll try to explain what this dynamic programming is through one example. I think that example you have already done in your previous course. Right? What is that problem? Problem is that finding nth Fibonacci number. So do you know what's this Fibonacci number? And have you done this coding of this? What is this? This is uh, nth Fibonacci number. So if I represent this as Fn, then there's a recursive formula for finding this Fn. So this Fn is like Fn minus 1 plus Fn minus 2. Right? Okay, so you have to just add the previous two terms and get the new term. Okay, and okay, so we have a base case with us. So we take both f1, f2 as 1, right? And then we get all the values like, so first one is 1, f2 is 2, then we have 2, then we have 3, then we have 5, and so on. Right? So I'm sure that you have written a code for this. So this, if I say 1, 2 is 1, and then if n is n minus 1 plus n minus 3, this is for all n greater or equal to 3. Okay. So for how do you write a programming for this uh, finding Fibonacci number, nth Fibonacci number? So I'll say, let's say, since I think you have already done this. I'm just writing. This is a straightforward recursive formula. You can use recursion, right? So this is the function name I'm saying. What's this? Fibo n. Fibo n is something like this. If n is lesser equal to 2, then f is equal to 1. Else f is Fibo n minus 1 plus Fibo n minus 2. Yeah, this is what I mean. Okay, is this okay? So this one. Oh, okay. So one more thing I'll do is just so this is the function return f. Okay. So this is the algorithm I think you all have done. Okay. Can you tell me what's the running time of this? Yes, running time of this one is 2 to the power n, right? And why is that? So as I said, like it's a recursive process. So this, if I take Tn to be the running time of finding nth Fibonacci number, so this is basically coming out to be, I have to know the n minus 1th Fibonacci number and have to this, right? So if I'm to solve this one, so I'll be getting something like exponential. Okay. Fine. Now, why is that happening? If I look carefully in the recursion process, so this is the first call that I'm making, and then I'm making two calls basically, Fibo n minus 1 and Fibo n minus 2, right? But this Fibo n minus 2 is again doing something else also. Fibo n minus, sorry, this is n minus 2 and Fibo n minus 3. And here also this there will be two subproblems as well. So Fibo n minus 3, Fibo n minus 4. And these will go on, right? Till we have Fibo 1 or Fibo 2, because those are the base cases, right? This is how this recursion works. Now, see one thing here. So when I'm finding, so you can see there are FIFO n is being called two times. So in this process, so this is one and this is another. FIFO n minus 2, that's being called two times basically. Can you tell me which one would be uh, which FIFO n minus 2 would be called first? Will that be the left one or the right one? Which call will be made first? This would be the call. Right? Now, so for this, you do a whole lot of things. So whole the many things you will do to find this one, right? And see, again, you will do the exactly same things for solving this FIBO n minus 2 again. Right. So basically, so if you think like this is repeated, so n minus 3 is also repeated. So obviously n minus 4 and all, many calls of the subproblems will be made repeatedly. So now what is an alternate option? The alternate option would be to uh, to use some table, right? And whenever I compute some value, for example, this FIBO n minus 2, so in that case, I'll store that value in that table. I'll maintain some kind of a table, right? So whenever I'm having some value for, suppose this is the n minus 2th value. So I'll store whatever the value is here, right? So what's the benefit of this? So next time when I call the same function, before going to the recursion process, I look into this table and check whether that particular value is there or not. If it is there, I'll just from this table, I'll get this value. There's no point of doing the same thing again and again, right? That indeed will bring down the running time of this process. You understand what I'm saying here? So since we are solving the same problem again and again, so to avoid that, what we can do is whenever we are solving a subproblem for the first time, I will store that result of that call. Okay, so that whenever I require it in the subsequent steps, so I'll go into that table and get that value from there. Okay, yes, I have repeated. Okay, so let me now just what I have just said, let's put into some algorithm. So what's the point here? Just a second. Yes, I'm telling you what I'm going to do. Um, okay, since you are asking, I'll repeat that. So since I'm solving this FIBO n minus two two times, right? So uh, here, so since this FIBO n minus two will be called first, I'll compute FIBO n minus two by doing all these recursive calls, the whole process that I'll do, right? And then I'll store the value that we get here. I'll store it, that value result of this in some table, right? So that whenever I require it for the next time, so I require this value at this point also. So instead of doing all this computation, I'll not do all this computation. So what I do, I'll go to the table and get the value from there. Okay, that's what I said. Now let's put this idea into our code. Right? So this will be another different algorithm. So I'll put as second algo 2. So again, I'll put the same name to this function. So I'll make a table, right? And I'll name that table memorization table, right? So it's memorizing the result of what we did, right? So first I'll initialize that table, right? So let's say I have zeros for all this. Now, when you are calling FIFO for some value n, so first thing I'll do that I'll look into that table and see whether that is there or not. So this piece of code is done outside this. So let me take it out of this. It's somewhere I have in the main function. Let's say I'm maintaining this table. Right? Yes. And so whatever you have said in the chat box, it's true. Okay. So FIVO n. So what I do, so I have this table with me. So whenever I'm calling it for the first time, I should be looking in that table. Right? So I'd say something like if memo n is available, then I'll return this value memo n. right? I'll return that particular value. Okay. So otherwise, what I'll do, if n lesser equal to 2, I'd say f is 1, else f will be, again I'll make this call, okay? Fn minus 1 plus fibo n minus 2, right? And then so I get this value. So fibo n minus 1, this is again, I'm doing some kind of a calling, recursion we are doing, right? And once so if we are doing something in here, that means this value is not available to me. Right? So I'll go into this if cases only when this n value for n is not available there. Right? So this is the first time I'm computing the value of fibo n, which is f in here. So since I'm computing it for the first time, now I need to store this value in that table as well. So I'll say in the memorization table for the nth value, I'll put this value f, right? And then I'm going to return f, right? Is this okay? Any question on this? Okay, fine. So now what is the benefit of this? So you'll realize the benefit straight away from this if you follow this recursion further down the line. Right? So okay. So let me do one more step. This is fibo. This will be n minus what? This will be n minus 3 fibo n minus 4. Right? Okay. So this will be again fibo n minus 4 n minus 5. It's fine. Something like this. Right? Okay. Now see, I have done this fibo n minus 2 here. I have calculated here and put this value in this table. So is it necessary to do the whole bunch of computation again for this one? I'm not doing it, right? So I'm just looking at the table and getting the value from there. So this whole branch of computation will be no longer valid for me. Okay? Okay. Now, what about this FIVO n minus 3? So FIVO n minus 3 is being called at this point for the first time. Right? This is the first call to the value n minus 3. And this is the second call to the value n minus. Not the second one. Maybe there may be some other. Yes, actually, it's a second call. Right? So I will do this computation of this in here, right? And store the value in FIBO n minus 3 in this, sorry, in this memorization table. I'll store this value. And when I require this value again, at this point, I'll get it from that table itself, right? So again, this branch of computation is also gone now. Right? This is the dead end, right? This is also the end of this. Similarly, if you do one more thing here, this will be for n minus 4 and this is for n minus 5, right? So again, whatever we will be doing here, right? This whole thing is no longer valid there, right? And in this way, so how does this recursion tree look like now? So it's a tree all the way will go up to the end. It's a three up to three I'll go, and then this value for at some point I'll go at some three, and then I'll get two, and I'll get one, right? Something like this. Let me redraw this portion here again. So it's three, I'll make a call two, and then make a call to one, right? And then this will be four. For four, I'll make a call. I'll put a box in, right? So I should be putting these boxes. This is two, this is one, right? Okay. Now what's the above? So this will be five. This is three. I'll put a box in. Right. So this will go all the way up to figure n. Right, you got this idea. So this will be the recursion tree of the second algorithm. Right? So you must understand that the second one is also a recursive algorithm. This one is a recursive algorithm. Right? Okay. Any question? This is how this recursion tree look like. Okay. Okay. So can you tell me in this part, right? Somewhere I put a square box and somewhere I put a circle there. Right. So can you tell me what are the differences of these? So what does this circle represent and what does this square represent? Can you guess anything? Yes, the squared one, the whatever I have put in the squared, those are the values that we are getting from the memorization table, right? From this table. And the circle actually means that I have to do something. I have to go through the recursion process to get to the value. So initially, what are the values that are there in that table? Initially, these were the values. For 1, 2, I have 1 and 1. Right? To get this value of 3, value for 3, I am doing recursion. That's why I'm putting it in the center. Right? So for 4, I'm calling this one, and then this value 2, I'm getting it from the table. Right? Okay. So you have correctly understood this. Right? So in this whole process, okay, I'm making a call to this function, fibo n. Right? I'm making some call to this function fibo n, but in some cases, I am actually uh, in some cases, what we are doing here, in some cases, we are actually going through the recursion process, and in some other cases, I'm just getting that value from that memorization table. Right? So this is recursion plus memorization. Memorization plus the recursion. This is the second algorithm. Right? Okay. And this is precisely This approach is known as dynamic programming. So what is dynamic programming in short? It's a recursion, and you don't do recursion for every value, right? If you see that the subproblems are kind of same subproblems that you are solving again and again in the process, so it's better to put the solution to the subproblems into some table, and that is called memorization table. Okay? It's recursion plus memorization. That's a dynamic programming function. Right? Now, what is the running time of this process? Now, the time complexity will be O of n. Right. Let's understand. So it's correct that it's now its running time will be O of n. Right. So let's understand now why is this running time is turning out to be O of n. And you'll see that when we have a recursion, when you have a dynamic programming, then the finding the running time will be very easy. So you have to understand just a few things, and then you can straight away mechanically you can tell. Maybe without even writing the code also, you can tell what would be the running time of the dynamic programming algorithm. Okay. Okay. So for that, we have to understand. So the recursion calls are of two types. Okay. So what are those two types? So something that I am drawing here. Right? Some of the calls are getting their solution from the table itself. Those I'll call the memorized call. Another type will be non-memorized call. Okay, memorized. What is this? What is a memorized call? Memorized call is basically something where you are uh, what I should say that memorized call. It's getting the value from the table, getting the solution from the memorization table. But in this case, we are doing the recursion. Okay, so these two types of recursive calls are being done. Right now, can you tell me how many non-memorized calls are there? Number of non-memorized calls. Yes, there are n of them. Right? So this is one non-memorized call. N minus one is one other one. N minus two, n minus three, all the way then five, four, three. Oh, basically it's n minus two basically. Right? I'd say, but still I'll say O of n, something linear, right? And these are precisely the, this is also, this quantity is same as the number of different subproblems that we are solving. Okay? So this thing will be important for us. Okay? So what are the subproblems for like smaller values of n? Those are the subproblems for this. Okay, it's clear? Right. Now, what is so and okay, one more thing you understand. So how much time do you take time taken in a memorized call? So how much time would you take to get to the answer for a memorized call when you are making a memorized call? Remember, memorized call is that one, the getting it from the table itself. Right? For example, this particular call here. How much time does this take? Just that memorized call. So what is happening? So this is a memorized call, one primitive operation. Correct. It's just time will be O of 1. Right? You have to just go to that table and get the value there. Right? So overall, so basically the in a recursion, in recursion, like that is non-memorized call. I'd say non-memorized call. Right? What is the work done outside recursion? Right. For example, what do I mean by this? Well, you understand this question? So suppose I'm calling it for 6. So this will be again called for 5 and this will be called for 4, right? And at this point, I know that this 4 is will be a memorized call. So that would take a constant time. Right? But for this, I have to do all this process, right? I'm not asking that. I'm asking what is the time taken for this? This is a recursive call, right? What is the time taken for this recursive call outside this recursion? So forget about this time taken in this portion. What is the work done outside this recursive call? This type of thing we have already done. So what is the thing that we are asking? This is a memorized, sorry, this is a non-memorized call. This is a memorized call. This is where this recursion takes place, right? And what is the work done outside this recursive call? This one, just an addition, right? So again, that's going to be O of 1, not O of n, O of 1 for one particular recursion call, right? You got this? Is clear? So in that case, what would happen? What would be the total running time of this process? So total running time will be the number of times we are actually doing this recursion. Right? That means the number of different problems, sub-problems that we have. Right? And for each of those recursion, sorry, for each of those recursions, whatever we have done outside this recursive call. Okay? So number of sub-problems that we have times the each in each these are the recursion these are the cases where this recursion is taking place. Other than that, I'm just getting the answer in constant time. Right? These are the cases where this recursion is taking place. That's basically the number of subproblems and this constant involved. So this constant is because of what is the work done outside those recursive calls. Okay? So that is for the intermediate step here. Okay, so that's the that that will be O of n. Okay? So the running time of this divide and conquer approach is O of n here. Okay, that's fine. Yes, so forget about the constant factor there. So since all those constants are already there inside this big O notation, you don't have to worry about it. Okay, fine. I can now this so let me write this fact here. So the total running time, how we are getting this total running time, it's the number of subproblems into time taken per subproblem. Right. Remember when we are counting the time taken for the subproblems, I'm basically counting the time taken outside the recursion. Okay. So it's fairly mechanical. So once I tell you the recurrence relation, you can immediately tell me what is this answer. Okay. So this recurrence relation also tells you that how can I convert this algorithm? This is algo 2 is a recursive algorithm, right? And with that, I am also using memorization as well. Now, this also tells you this recursion tree in here also tells you how to convert this recursive algorithm into a iterative algorithm. Okay, so I can convert this one as a iterative algorithm as well. So what I do instead of calling the FIBO n for the first time, so what I'll do, I will just think about this memorization table. Let's call this FIBO table. So let's say they are starting from 1. So I know these value. So then what would be the third value? I have to just add these previous two. And what's the fourth value? What's the fifth value? Something like this. Right? What I'm doing? So earlier, what was happening? What was the first call that we made earlier in the second algorithm? So this one was the first call. To get to the answer, we made a call to this as well as this, right? And again, to get to this particular value, we made a call to this one and this one, like this, right? So eventually we kept calling these functions till we get these values. Right? Once I get these values, then I'll go in the forward direction to get this value. So since we are recursion tree says us that instead of first coming in this direction and then getting the solution from this direction, why not start from this direction? That will give you a straightforward iterative approach. You understand this? Okay. So let me write it into a code of what I'm saying here. So I'll call it algo 3. Again the same approach. Right? So same name I'll put it. Right? And let's say I maintain this table, memorization table. I'm just putting some name to it. To go. Right? Okay. So what I do, I'll use a for loop for k runs from 1 to n. If k lesser equal to 2, then I'd say f equal to 1. Else, I'd say f equal to pivot uh, k minus 1 plus pivot k minus 2. Right? And then once I get these values, then I'll write pivot k is equal to f. Right? And after this, I am going to return this value. Return pivot n. Okay. So if for this values k equal to 1 to uh, 1 to n, I'm going to do this. Right? Initially, I know what are these values. K equal to k for 1 and 2 is going to be 1. Right? Otherwise, I'd say that f will be pivot k plus 1. So see here that when I'm making this call, I know this value as well as this value. Right? This is the table itself. This is the table itself. So table I should write capital F. Right? So this capital F, again this one is capital F. Okay, you got this? Is this algorithm a recursive algorithm? This is a recursive algorithm. Sorry. No, this is not a recursive algorithm. Right? This is what type of algorithm is this? What type of, is it a recursive algorithm? So are we doing any kind of recursion here? Recursion means, so to get to a value, so I'm going to ask the previous value. Again, ask the previous value. Yes, this is an iterative approach. It's an iterative process, right? And this type of iterative process is also known as dynamic programming, but says there's something different. I'll call it something different than just dynamic programming. I'm going to call it bottom up dynamic programming. See, why are we calling it bottom up dynamic programming? So if it's a recursion, so you should, if you look at this recursion tree, I should be coming from the top to the bottom, right? Top to the bottom. So I'll make this, so same in here, right? I'm coming from top to the bottom. Now, when I'm converting them in the other other way, so what is the first call I'm making? This is the first call I'm doing, right? So I know the value of 2, value of 1. I'm trying to figure out the value of 1. So then I'm finding the value of 3. So in this tree, if you see the recursion tree of this previous process, in the third algorithm, we're actually going from the bottom to the top. Right? Still, we are using some kind of a memorization involved in it, right? That's why we are actually calling this. This is also a dynamic programming, but we'll call this one as bottom-up dynamic programming algorithm. Okay. So what's the difference between algo 2 and algo 1? The main difference between algo 1 and algo 2 and algo 3 are the order in which we are solving those subproblems. Is it okay? Any question? So, okay, is your screen shows? No, I think it's okay, no? Any question? So that was a dynamic programming for okay, fine. So since this example was quite, I think it's since you have done this before, so you understood this problem very well. Now let's take uh, another example. Okay. So what is this problem? Let me tell you. So I'll say this is the maximum non-consecutive sum problem. So what is this input to this problem? So I'll give you an array of n numbers. An array of n non-negative real numbers. Let's say they are in this A1, A2, AN. So I'm going to output uh, the maximum sum. Yes. sum of non-consecutive real numbers from the array. So what do I mean by non-consecutive reals? Non-consecutive reals means like they should not appear consecutively in that array. Consecutively means like next to each other. Okay. So for example, if I take just a simple say one. So what would be the set which would give you the maximum non-consecutive sum? Yes. So basically from this set of numbers, I have to pick a subset whose element sums are maximum, and also none of the values are consecutive in the array. So that means like in this case, I would be taking like 4 and 4, right? If I take those two fours, then the sum of that subset is 4, and that is maximum which is possible to maintain this non-consecutive property. None of the elements from the set should be consecutive. Okay, is this problem statement okay? So in this example, our output is this 4, and the set, any two numbers should not be consecutive. Any two numbers should not be consecutive, yes. Like, the set that we are choosing in the output, I have to take such a set where none of the numbers are consecutive. The set basically will be having, if I say it's an array, let's say this is A1, A2, A3, A4. What is that set basically? This is A2, A4. Okay. Any question? Yes. Okay. So I think you have understood the problem. Right? So we are going to design a dynamic programming algorithm for this particular problem. Okay. So first thing, so we have to come up with to design a dynamic programming. So it's basically a recursion, right? Clever way of doing recursion you can think of. Hmm. So to come up with a recursion, I must have some kind of recursive formula. Okay. So first, I'll try to uh, analyze the solution and try to figure out a recursive formula for that solution. Okay, fine. But in our previous example, that was not the case, right? Because for Fibonacci numbers, I know what's the recursion, right? And so that was already given to us. But for this problem, it's not very clear what that uh, recursive process would be or the recurrence relation would be. So what's the question? Each And each and every element should be in output array from the input array. Yes, I have to basically pick a subset of these inputs such that no two numbers in our subset is from this. No two numbers are consecutive in the array. Okay, does this make sense? Is it clear now? Okay. So first, we'd like to, so what we are trying to do here. So I'm given, so I'm trying to find out the solution for this. So let's call the solution as let's say Wn. Okay. So what is the solution? Let me put some name to it. It's a maximum non-consecutive sum of n numbers. Okay. This is what the algo name I'll give. So it's a function basically, function of n, right? Maximum non-consecutive sum of given n numbers in an array. Okay. Let me call that is the solution of Wn is the solution of maximum non-consecutive sum of n numbers. Okay. So I must understand how does that solution look like? So basically, what is the solution? It will be a subset, right? So uh, any solution S, right? It's basically a set of numbers from the array. So any solution, I'm going to condition it on the last element. Either contains the last element A1 or does not contain. Okay. So if I have, if you give me this A1, A2, A3, AN, let's say AN minus 1. Okay, any solution you give me. So that tells you what? It may contain this last element, or I might get a solution that it doesn't contain the last element. Any solution would be either of containing AN or not containing AN. Right? And let's try to see what are these cases. Under these two cases, AN, suppose this AN does not belong to the solution. Okay. So if AN, the last one, is not in the solution, then what can I say? Can I say that S is a solution of some subproblem? So then, what can I say? S is a subset of A1, A2, AN minus 1. Is this clear? So all the elements of S must be from a1 to an minus 1. Why? Because an is not in the solution. We are assuming that an is not in the solution. Right? And also S gives maximum non-consecutive sum of the elements a1 to an minus 1. Right? So that says what? S is also a solution of which problem? Uh, Always I'm writing. So it's maximum non-consecutive sum, maximum non-consecutive sum of how many elements? What should I say? N minus 1 elements, right? So when S is not, so we started with S is a solution of this maximum non-consecutive sum when we have n elements. We are assuming so that there are two cases. Either S contains the last element or S does not contain the last element. We have taken this case first. So suppose S does not contain the last element. So the elements are coming from this set, and this also gives you the maximum, right? So basically S is a solution of maximum non-consecutive sum of n minus 1 elements. Is this clear? Okay. Now let's understand the second case there. An belongs to S. What would happen in this case? Let's again draw. I have An. An is this one. Right? This is in the solution. What does that tell you? That implies that An minus 1, is it in the solution or not? What about An minus 1? If An is in the solution, so it's n minus 1 is not in the solution. Correct? So this also implies, think about the elements other than An, elements of S other than the last An. These elements are coming from what set? Something similar to this one I am asking. So the other elements of S are coming from which set? Yes. They are coming from n minus 2 up to n minus 2. Yes, because as I said, like a n minus 1 is not in the S, right? And I have also taken a n out. Right? So all the elements are coming from here. And also, and this S minus a n leaves the maximum non-consecutive sum of a1 to an minus 2, right? So how does this solution look like? So this is basically a solution S minus an is basically a solution of n minus 2, right? So this actually gives you a solution for this, a recurrence relation. This is this clear? This case one and case two. Any question? Okay. So this actually gives you this recurrence relation that I was asking. Let Wi be the maximum sum of non-consecutive elements of the array A1 to AI. Okay? Suppose Wi is that number. Right? Then how can I write this Wi? Wi will be either Wi minus 1. This is the case when this an is not in the solution or ai is not in the solution. Right? Or in the other case, it's a wi minus 2 plus this ai. Okay? This is the recurrence relation that I have. Okay? So, and at the end, so for I equal to 0, what would be the value? I equal to 0 means, so I equal to 0 means I don't have any element there. So that W0 will be 0. And I equal to 1 means what? I equal to 1 means I have only one element, and that itself is that non-consecutive one. So that element, if that element is an, so the solution will be a1. Okay. And what is the problem that we are solving? We are actually solving when the array size is n. So we are actually trying to solve Wn. What is the value of Wn? So again, I'll get it from here. Wn minus 1 and Wn minus 2 plus an. Right? I'll take maximum of this. This is the recurrence relation that we have. Is this clear? Can you understand this? Okay. So once I have this recurrence relation, then I can straightforward write the recursive algorithm for this maximum non-consecutive sum. Right? So it will be again similar to the first version. Right? So maximum non-consecutive sum of n elements. So what I do, I just basically it's a copying of this recursion here. Right? So it's like if n equal to 0, then return 0. If n equal to 1, return that particular value, a1, else return maximum of wn minus 1 and wn minus 2 plus an. Right, so basically what are these? So not I should be writing in terms of the same function MNCS n minus 1 MNCS n minus 2 plus an. Right? This is the okay. So it's a straightforward the recursive process. Right? So what is the running time of this one? N to the power 2 is basically like no, 2 to the power n. Okay. It's exponential running time. It's the same as the first version of Fibonacci number that we have written. See, exactly same. So here also I have two base cases like n1 equal to for if n equal to 1, then f equal to 1. If n equal to 2, f equal to 1. Else this. The same thing. Right? It's 2 to the power n exponential running time. We have almost similar thing there, except there's some addition I'm doing here. Right? It's exactly same. Or so since in one case I'm doing this addition, and I'm instead of adding these two, I'm taking the maximum of these two quantities. Right? And that's the difference there. Okay. So it takes exponential time. But again, if you draw the recursion tree, you'll realize that the same subproblems we are solving again and again in this approach. So what's the better approach of doing it? Using memorization technique. Right? Just by before I write the second version of that process, I'd like to ask you about the running time of the dynamic programming. So second version is the dynamic programming approach. Right? So can you tell me before writing the algorithm even, a pseudocode of the algorithm even, can you tell me what would be the running time of this process? O of n. Okay, n. Why is that? Uh, Bucket sort. So this. So let's finish this, and then after this, we'll discuss whatever queries you have. Okay. Uh, yes. What's the running time? It's saying O of n. Why is that? I I want you to think according to this line. How many subproblems do I have? Number of subproblems. Number of subproblems are O of n. And time per subproblem outside the recursive call is this. So whenever we are having some recurrence relation, you have to understand how many subproblems you are solving there and what is the work done outside the recursive calls that are doing here. Like if you understand those two things, of course, there is something else as well. But if you mainly understand these two things, then you get the uh, you can tell what's the running time of this process, right? Now let's quickly write the second version of this. The maximum non-consecutive sum of n elements. For this, again, we are going to store this memorization will be stored somewhere. Okay. So again, so first thing I should do, we should look in that memorization table. If this is available, then return that particular value. Else you do something. Right? So if n is 0, return 0. If n equal to 1, return a 1. Else w equal to make w equal to max of MNCS n minus 1, MNCS n minus 2 plus AN. Right? And after that, I'm going to store that particular value in WN and then return that. Right? That's the same as before. See, one thing very interesting here. So this part of this code is exactly same here also. Right? Okay. So again, you can write the third version or uh, the bottom-up dynamic programming as well. So this is the dynamic programming algorithm, and third algo is the one, the bottom-up DP. What is this bottom-up DP? So you have W0 as 0, W1 as A1, right? And for I runs from 2 to n, you write Wi is just that recursive formula you write. It's between Wi minus 1 and Wi minus 2 plus Ai. Right. Again, this part also it's exactly similar to the recursive process. Right. Only thing is that you have to figure out this ordering. You have to channel the subproblems in such an order that it follows this uh, the order of the subproblems that you are solving that you have to manage. Okay. So is this find any question about this dynamic programming approach? Yes, any question? Okay. Okay, fine. So, we'll do a few other examples of dynamic programming, but that I'll do in the next class. Uh, Fine. Okay. So that is all. Okay. So now you can ask any other question that you want. Okay. Yes.